So the main application of recurrence relations, and the reason we want to set it up like we do as opposed to the way we have done previously in terms of the formula at least, is to find what we call the limit of the sequence. And this can be used in a number of different aspects, and this is partly why it's used in medicine and it's used in kind of populations and so on and so forth. But what we basically want to do is we want to find out what happens to the sequence as it gets bigger and bigger, as it gets further and further through that sequence. Okay. So you'll see a lot of notation surrounding this, and this is where it gets a little bit confusing. But the idea of the limit itself, or the way we find the limit, is actually quite straightforward. So don't get yourself bogged down too much in, as I say, the notation surrounding this. Okay. But it's often very useful to examine what happens to a sequence as n, so the term in the sequence. Okay, so the different terms that we're dealing with, so un plus 1, so all those different terms get very large. Okay, so we've got the first term, the second term, the third term, the fourth term. So as we get further and further through them, the n gets bigger. Okay, so the bigger that gets, the closer it gets to infinity. And this is what we mean. This is described mathematically as n tends to infinity. Basically what we're saying is as n gets bigger and bigger, as we get further and further through the different terms in the sequence. That's all that means, okay, as n tends to infinity. But we write it in the simplest way is just like this, as n tends to infinity, okay? So with each sequence, okay, with any sequence, as n tends to infinity, there are three different types of behavior. So there's three things that could happen to the sequence, okay? So the first one, okay, as the sequence tends to infinity, what can happen? And these are basically these are just the different terms in the sequence. So the first term could be this one, second term, third term, fourth term, fifth term. As you can see, it just keeps going up in a straight line. Okay, and that's generally what we've looked at thus far, in previous years at least. So basically, we've already looked at a couple like this. The kind of the difference between them is exactly the same. So we go up by 3 each time, in which case we form a straight line. Okay, in the same way, okay, the sequence can tend to negative infinity, in which case basically just decreases, okay, but still in a straight line. But the one that we want to look at, the one that we're most interested in, is when the sequence converges, what we call to a real limit. As I say, don't worry too much about the notation and the wording around this. What it all means is that something like this will happen. So as it increases, okay, it actually almost kind of tails off, okay, and it flatlines, okay. Basically gets to a point where it just stays the same, and that's what we call the limit, and that's what we're interested in. That's why we kind of use recurrence relations, because we want to find where this occurs. Okay, so the notation around this is in the recurrence relation. So a standard recurrence relations are just the ones we've been looking at. Un plus 1 equals some number times by un plus some other number b. This is just the kind of standard notation. The first thing we need to know, and this is really, really, really important, it's so important I'm going to underline it with 2 red lines, okay? For a limit to occur, the number a, so in other words, the bit that we're multiplying un by, has to be between -1 and 1. And notice that the lines can't be equal to -1. So it's -1 is less than a, so a is greater than -1, not greater than or equal to, and it's also less than 1, not less than or equal to 1. So anything basically between -1 and 1 for the value of a means that a limit will occur. Okay, so for example, if you had un plus 1 equals 2 un plus 3, a limit would not occur. Okay, it would basically be one of the first 2 examples that we looked at there, where it would just keep increasing and increasing and increasing. It would never kind of flatline. Whereas if it was, say, un plus 1 equals 0.5 or 0.6 or minus 0.3, un plus some number, doesn't really matter what number that is, okay, a limit will occur, in which case it will flatline, it will just kind of curve out to a point, and it will just stay at the same value. Okay, and that's what we're interested in. And when that happens in a lot of different, as I say, mathematical applications, okay, that's quite useful to know. Okay, if we're going to find the limit, if you're asked to find the limit, you have to state this fact. Okay, because what's going to happen? We're going to give you a formula, and the formula will still work. Okay, this formula will still work if this number a is out with this limit. So if a was 2 or -7 or whatever, the formula will still work. It will still appear to find you a limit, but it won't actually be a limit. Okay, so the first thing you want to do if you ask for a limit is determine basically if this value a, so in other words, what we're times un by the coefficient of un. If it's a number between -1 and 1, then a limit will occur, and we can proceed to actually find the limit. If you don't do that, if you just ignore the fact, ignore what this number is, and if it is a number that's out with that limit, you'll still appear, as I say, to find a limit, but it won't actually be true. Okay, so you have to state this fact. You have to actually write this down. Right. This next bit is basically going to show you how to find the formula. So this is one I always struggled with. I always forgot this formula when I was growing up. Okay, and I used to basically use this to work it out. So what's basically happening here is we want the limit will occur when one value is the same as its previous value. Okay, in other words, where un plus 1 is actually equal to un. Okay, and given that, we can actually rearrange this to find out what that un is. That's going to be our limit. Okay, so that value, whatever it is going to be our limit. So when the next value in the sequence is the same as the previous value in the sequence, we have reached the limit. Okay. So in terms of the standard formula, this would mean that un was equal to a un plus b. In other words, as I say, the two values are exactly the same. Or more specifically, as un is now the limit of the sequence, we can say that L would equal AL plus B. Okay, this is more commonly rearranged into the following. So we can rearrange this formula into this formula. Okay, going through those processes. So if you forget this, and this is a formula that you will need, and I pretty much guarantee 90% of the time in your exams, you're going to have to use this formula. In other words, you have to memorize this formula. If you can't memorize it, you can work it out just from your basic kind of recurrence relation. Okay, so L equals AL plus B. So limit occurs when basically these two values are exactly the same. And what we want to do is we want to find that. So we need to take everything to one side and factorize, just so that we've just got the one L. Okay, so take L as a common factor, 1 minus A, and then we can divide by all of this, in which case L equals B over 1 minus A. And this is your formula now to find the limit of a sequence. Okay, but just remember, it can only actually work if the A value is between minus 1 and 1 as stated above. Okay, as I say, if it wasn't, you could still put it in this formula and you could still find a value for L. It just wouldn't actually be a limit. You're just finding some random rubbish. Okay, so the first thing you want to do when you find the limit is actually state this fact, and then you can proceed with this formula. Okay, all right, so an example. Explain why the sequence defined by the recurrence relation un plus 1 equals 0.7 un plus 15 converges to a limit as n tends to infinity, and find the value of this limit. All right, so this first bit is a clue. So explain why it has a limit. We won't always be told that, but in order to explain why it has a limit, it's the fact that this number here, the coefficient of un, is between minus 1 and 1. Okay, so a limit exists as 0.7 is between minus 1 and 1. So because that value there is between minus 1 and 1, there is a limit. And that's all you really have to do for the first bit. But even if you're not asked that first bit, you still have to state this fact. Okay, so just write this down every time you're dealing with a limit. This number here is between minus 1 and 1. Write it down. That means that a limit exists. Okay. Now, in terms of actually finding the limit, we need that formula. Okay. So the limit is b over 1 minus a. Okay. And then it's just a case of putting in these numbers. Make sure you put them in the right order. A comes before b. This is our a value. This is our b value. So it's going to be 15 divided by 1 minus 0.7. 1 minus 0.7 is 0.3. And 15 divided by 0.3 is 50. Okay. So the limit of the sequence is 50. Okay, right. What that means, as I say, is that it will kind of flatline at that point. Okay, so the highest value that it gets to, or where this sequence kind of ends, at least, is at 50. Okay, so if we want to put that into a situation, it can be quite useful. And this is kind of a situation that's used quite a lot. It certainly comes up in exams quite a lot. And I'm not saying that you're going to get into a job where you're an environmental activist. Some of you might already be that. But nonetheless, it can be quite useful to find out what the limit is in a situation like this. Okay, so a chemical factory wants to dump 200 kilograms of waste into a sea lock every week. Okay, very bad, but nonetheless, it is estimated that the tide will remove 65% of this water each week. Environmental groups claim that more than 350 kilograms of waste in the lock will be harmful to the local sea colony. Okay, I'm pretty sure any amount of chemical waste will be harmful, but nonetheless, is it safe for the factory to dump the waste? Okay, right. What this basically means is this doesn't say anything about recurrence relations, it doesn't say anything about limits, but we want to basically find that if there's 350 kilograms of, if we want to work out if there's 350 kilograms of waste in the lock on a more kind of permanent basis. So if they're dumping 200 kilograms in, okay, it would appear that after kind of 2 dumps, it is going to be more than 350. But the idea is, as I say, of the tide, is that it removes part of it. Part of it is gone. So actually in the lock at any one time, there won't necessarily this is what we're trying to find out, necessarily be 350 kilograms. But if we can work out, if we can determine what the limit is, we can work out a sequence first of all and determine what the limit of that sequence is, then we can find out if this is true or not and whether it's safe for the factory to dump the waste. So the first thing we want to do is actually put all this information into a recurrence relation. So what we're basically saying, this is 200 kilograms. That's what's going in. That's our kind of B value, okay? But then 65% of that is removed. But remember what we've got to do. We've got to work out how much is left in relation to the previous amount that was there. Okay, so what this means is that 35% will be left. So the next week or the next time they dump the waste in, there'll be 35% of what was there previously, plus they'll dump an extra 200 kilograms in. Okay, so initially there's obviously nothing in there, so U0 would be 0. Okay, right. First thing we can do, if we're trying to actually find the limit, we want to determine whether a limit actually exists. So because this value, the 0.35, is between -1 and 1, there is a limit and it does exist. Okay, we have to make that clear every time we're trying to find the limit. So 0.35 is greater than -1, it's less than 1, it's between these values, so we know a limit exists. Now we actually want to find that limit using the formula. So remember, B over 1 minus A, B is 200, A is 0.35, so it's 200 divided by 1 minus 0.35, and you can put that in a calculator. Right? What that tells you is that the limit is 307.69 kilograms. Okay, so it will kind of consistently be 307.69 kilograms of waste in the lock. So what's going to happen is that the tide's going to remove 65% of it, and they're going to put 200 kilograms back in, and that'll just even out at around about 307.69 kilograms. Right, so then we actually have to answer the question. 307.69 kilograms is less than the 350 kilograms that they say will be harmful. In other words, it's safe for the factory to dump the waste. Obviously, there's a lot of problems with this question. I can't imagine you get a question like this anymore because we don't like this kind of thing, but just roll with it, okay? But again, the difficulty of this question is establishing that it is a recurrence relation question and it is a kind of a limit that we're looking for. Okay, and that's the difficulty that will come, but a bit of practice and you'll be able to see that, okay? Right, this last question, I'm just going to leave this up. I'm not actually answered this, but if you want, you can kind of email me and I can send you an example. This is the question that caused a lot of outrage a couple of years back in the exam, and everyone signed a petition. Everyone was whinging and whining on social medias and Bebo and stuff about this question in the exam. First thing you notice is question 3. Question 3 means that it's a relatively straightforward question, and it is a relatively straightforward question. I think people just basically read the first line and thought, oh, if it's the 16th century, this must be impossible. No one's been able to answer it for 400 years. This is really difficult, but it's actually a really straightforward question. But the idea, again, similar to that last question, is it doesn't necessarily tell you that you're looking for the limit. But with a bit of practice, you can think about what's going to happen here, okay? But what's happening with a frog and a toad is they're jumping up and then falling down a little bit, jumping up and then falling down a little bit, okay? And each day that happens, they jump a little bit further and then fall down a little bit further, in which case they're going to reach a limit. They're going to reach a point where they don't actually climb any higher than. So the idea is, what we're asked for is, will they actually escape the well? Okay, so what you need to do in each of these cases is you need to find the limit of each of these recurrence relations and work out if the limit is basically bigger than 50. If it's bigger than 50, then they'll get out of the well. If it's less than 50, then they'll be stuck in that well, jumping up and down for forever. Okay, so give it a try. This is an exam question, as I say, yeah, email me if you want some help with the answer. Okay, but it is a lot more straightforward than it perhaps appears. Don't be put off by the fact that it's appeared in the 16th century.